Elsa Olivetti, who is a professor in material science and engineering. She's a person with extraordinarily broad interests. I think I first got to know Elsa when she was bringing AI methods to bear on understanding materials scalability for energy applications, which is a really important area. But she keeps doing things that are central to energy, and so we keep trying to engage Elsa in programs we're doing. She spoke yesterday at a future of storage external advisory committee meeting, and has really interesting things to say about supply chain. So let me not take up your time, Elsa. Turn it over to you.
So much for joining, everyone. I'm grateful for that opportunity to share some thoughts on material supply chain considerations, particularly related to the energy transitions that Bob talked about early on, and links to the future of storage study. So as folks know, many of the technologies related to decarbonization are enabled by or directly designed around particular sets of materials, and therefore we're subject to the supply chain issues that accompany those materials. And so we try to understand the development of those new technologies in the context of how that links them to these supply chains. Chris's talk was marvelous in that it directly talked to the pressing issues at hand. I'm not going to talk so much directly about that, but you hear material supply chains coming up in the current conversations, particularly around the Defense Production Act, and our ability to address mining and production of minerals domestically that are considered essential to the nation's security. And maybe another implication of the current crisis has to do with our further how we treat the relative domestic versus global nature of our supply chains and the kinds of pressures that puts on us. And maybe again another reason to be concerned about decarbonization, right? As we try to pull things more domestically, that's going to change the economics of the situation and may change the nature of those learning curves and manufacturing capabilities that Chris spoke to. So I'm not going to focus so much on that, the current crisis and what I'm going to talk to you about today, but this idea between balancing how we source our materials, the need for stable supply, but the broad implications of the materials, metals, and recycling industries is something that I'd like to bring up for everyone today in terms of what we're talking about here. So from a big picture perspective, should we worry about the nature of our supply chains and the sustainability of our resource supply? And from a general economist perspective, as we would say, we would use more of a particular material that will lead prices to go up. As prices go up, then that's going to mean that we then use less, or we switch to other resources, and things would generally sort themselves out over time. And what we try to understand is that the more short-term implications on firms, on industries that aren't prepared, on the nature of the supply chains and the development of new technologies that may be impacted by the kinds of short-term or medium-term implications that Chris spoke to, and that that we see have influenced things in the past. And so when I'm talking about material supply chains, I'm not talking about, are we running out of a material? That's not the question. The way we like to frame it has more to do with risk, and is a particular risk perceived or actual too high to a decision maker in order to advance a new technology. And so beyond this, do we have enough question, particularly around energy storage on the grid or electrification of the vehicle fleet? There's a set of nuances around the market imperfections that would be particular to a particular material. Are there substitutions in terms of the function of a material? What are the feasibility of alternatives, the relative importance of the technology? And then from a material science perspective, what's the nature of how we extract that material? So this is sort of the balance that we're interested in looking at here. And we can look to historic examples, just very briefly of how these sorts of supply chain disruptions have impacted price and potentially technology in the past. Just two quick examples here. One, cobalt in the 1970s, where despite having less than a tenth of a percent of the population, the Democratic Republic of Congo controlled 40% of the cobalt resources. That's still the case in large part, and just a small scale rebellion in that country led to the price excursion that you see on this plot here in 1977. And even though price comes back down, it changes dramatically the way that supply chain responds to the use of that material. A slightly more recent example, in 1997, Russia in its production of palladium. We're looking at palladium demand over time, and we see the particular end uses of palladium here in red. And in around that time period, Russia controlled about 40% of world production of palladium. They cut production. You see the price excursion here, and in this case, it was a substitution that was made, material substitution between palladium and platinum, particularly in the automotive sector, which is this bottom area plot here. And so we see after that price excursion, then the use of palladium in auto catalysts goes down, and many decades later comes back to that same level. So broad implications even though the price changes are temporary, effects to firms are permanent. So that's the kind of historic example that we're interested in, and how that might inform our thinking about resource availability or materials criticality going forward. So we try to think about this as, what are the materials we're using, and where do they come from, and are there particular risk factors present? Risk factors might have to do with the geographic concentration, as I'm sure folks are familiar with, the particular growth in new technologies, what's the recycling like for that particular material element. And so these are the kinds of factors that we look at in terms of screening where might there be supply chain risks that would have a particular implication. But these systems are dynamic, so we have to also look at them in terms of scenario analyses. And so why do we particularly care about these materials concerns and to the scaled impact that what the impact that might have on our ability to decarbonize or our ability to develop new technologies? And so I'm going to just give you this example around analysis of materials used in lithium-ion batteries. We could look at many supply chains for energy relevant materials, but given the demand growth for lithium-ion batteries, as Bob spoke to, the role in the in grid-based storage, but also maybe to Chris's comment about changing modes away from public transportation. If we can electrify the fleet, maybe that still lets us decarbonize. But what sorts of materials implications might there be, or supply chain implications of that scaling? And so the direct implication of disruptions in supply chain, relates to price, right? Relates to the price of that technology. And so this work on this slide was by Professor Yet-Ming Chang and Professor Bill Green at MIT that particularly looked at learning curves for battery price over time. And so we see this base case scenario here that over time, maybe our battery pack price by 2030 gets to $124 per kilowatt hour. But what they looked at was a series of learning curves in the learning for battery pack production, but they decoupled the materials impacts, and that we see in this green line here, the learning curve for the materials components of the batteries, and just below it is the elemental prices or elemental learning curves. And we see that in some ways that there may be this practical limit that's set on a price of technology based on the supply chains of those materials. So as there's perceived shortages or disruptions and those prices start to go up, that can really have a direct impact on the technology. And that's why we're particularly interested in it from the perspective of decarbonization. So the way we want to look at this, and particularly trying to screen where are there potential supply chain challenges for lithium-ion batteries, is first we need to understand how much of a material is used in a particular chemistry or particular battery chemistry. So here I'm showing a set of lithium-ion chemistries here, and then their elemental content of lithium, cobalt, nickel, and manganese, and then their dominant use in electronics for the case of lithium cobalt oxide, and then auto and grid-based technologies for the other chemistries. And I don't mean to suggest that these metals are used as is in these technologies. Obviously, they're used in their precursor forms to produce cathodes that are relevant, or in the electrolyte cases as well. But we track the data from an elemental perspective. And so the key message from this slide is that the material intensity is going to vary by technology. So in particular, we think about cobalt, varies by an order of magnitude across these chemistries. And so when we think about the scaled implication of vehicle electrification or more use of storage on the grid, we need to understand in detail what chemistries we're using and how that might evolve over time, because that's going to change the amount of overall material we want. So as I said, cobalt varying pretty significantly, but nickel as well, particularly as we consider shifts between more nickel-based and cobalt-based technologies. So from this sort of a screening, we're going to look further at lithium, cobalt, and nickel in particular to try to understand what the supply chain implications of scaling those technologies are. So here are just another set of metrics that we've looked at. As I said, I would like to focus here on lithium, nickel, and cobalt. And what the plot I'm showing on the left is looking at the reserve, so the amount of economically extractable material at the time of these numbers divided by the annual production. So in some way, you could think about that as a years to depletion, a static depletion index. And as I said, it's not about running out; it's about what are the perceived risks associated with that. And then on the x-axis here is the fraction in the top country for that particular element as mined. So this is getting at those metrics of geographic concentration that I mentioned. So just to draw your attention to this, nickel and manganese here used predominantly in steel are pretty stable over time. Oh, excuse me, I forgot one more detail, which is that for each of these elements, I'm showing 3 time points, 2005, 2010, and 2015. So you see these move over time, and that's, as I said, this reserve number is an economically extractable number. So that's going to shift depending on the price of those elements and you know, on the supply curves for those materials. So we see the kind of trends that are interesting here is that nickel and manganese are relatively stable, relatively diverse in terms of how much they're extracted in a particular region, and that has to do with the maturity of the markets that they're part of in steel, as I said before. Versus lithium, over time, we've seen, you know, as there's been more demand, the reserve numbers have gone up. So there's been more that's been economically extractable, and it's also become slightly less geographically concentrated, not dramatically so. So that's sort of a you know, indication that there's sufficient supply to keep up with that, and robust supply chains to keep up with that demand, versus cobalt that's moving not only more concentrated in terms of the fraction produced in a particular country, but also that, you know, is moving down on this static depletion kind of index. And on the right here, I'm just showing the top country in terms of extraction. And as we know, and I'll show briefly on the next slide, that there's a particular geographic concentration, as I said in my historic examples, in the Democratic Republic of Congo. So comparing geographic concentration just briefly, you see very clearly on this map, I'm showing trade flows of cobalt on the left, highly concentrated. That thick flow we say there is from the Democratic Republic of Congo to China, so concentrated in terms of extraction, but also refining, and this is in US dollars. And on the right-hand side is a much more diverse supply chain for lithium. So just, again, a snapshot of you know, relative concerns around materials availability that could lead to challenges in price impacting technology. The advancement of technology. As folks likely know, lithium is not only diversified geographically, but it is also diversified in the way we extract it. So extracted from brine flows as well as a mineral-based form. So that's another source of diversity that means that those supply chains have some more resilience. So in addition to cobalt being geographically concentrated, another one of those nuances that's connected to my Venn diagram there that I showed you earlier has to do with the nature of how the material is extracted. From the kind of how does a mining company derive revenue from a particular mining project. And in the case of cobalt, it's mined as a byproduct, primarily from copper and nickel. So rather than a mine being in existence for the revenue of cobalt, primarily it has to do with the revenue derived from these other carrier metals instead. And what that implies is that an increase in price for that particular material doesn't drive supply necessarily, because the supply is governed by instead the dynamics associated with that carrier metal. Versus if it's a little bit more of a co-product status, then that, you know, means that there may be more responsiveness in that supply chain. There are differences between the carrier metal relationships that I show quantitatively on the right-hand side. There's a lot going on in this plot, but I just want to draw your attention to one thing. What we're plotting on the x-axis is the byproduct fraction. So for a particular pair of byproduct carrier metals, how much of that byproduct is coming from that metal versus the value ratio, which is about the price, it's about the concentration in the ore. And so as I told you, there's a difference in the nature of these carrier relationships for cobalt and nickel. So nickel's the nickel cobalt pairing is much lower on this value ratio axis than the cobalt copper relationship, meaning that that it's much more of a byproduct relationship when we're talking about nickel. And this is significant, as I'll show you, because of some modeling work that we've done to try to say, as we have increased demand for lithium-ion batteries in storage or in electrification of the vehicle fleet, how is that cobalt supply going to respond? And so this is a plot showing the nature of that cobalt supply going forward geographically on the left-hand side, where we're looking at production share and mining production, and then by that principal metal, so by where most of the revenue is being derived from a particular mining project on the right-hand side. And so we see a couple of things here. So on the right-hand side, we see that the production going forward is largely still focused in the Democratic Republic of Congo, and then even the rest of Africa here, if you can link those two bars in your mind, and also growth in Asia. And on the right-hand side, we see going forward that we would have still a lot of cobalt derived from these mines that are in existence primarily for copper, but that this nickel section grows. And the difference in coloration here is the solid bar has to do with announced mining projects versus those that we simulate that are in this hashed form based on the nature of the deposit and the feasibility. So the overall growth in nickel, we think, is significant because, as I told you, that value is lower, so that fewer of those projects would be governed by or driven by increases in demand for cobalt in particular. So just to kind of close this story on the cobalt side, here's a scenario that we did in looking at cobalt supply versus demand in 2030, where we have just two different demand scenarios. I focused on the demand in decarbonization, so related to automotive battery production, but also other battery production. There are non-battery applications of cobalt that are particularly, that would probably not respond too much to changes in price. The super alloys used in aircraft engines, hard cutting materials, etc. And this big bar here is primary supply. And so we see that the primary supply is likely to be able in the short term to meet the needs of demand across a set of low and high demand scenarios. But the nuances that I presented around this shift to nickel are significant in terms of the potential price implications of that. And then the final little point here to make is this little sliver of a bar here on the top is related to secondary supply. And so it's important to think about what role secondary supply might play, meaning recycled material, that we're able to recover from spent batteries. And the challenge here has to do with the timing of that. So you saw that purple bar was a pretty small part of our ability to meet demand in terms of cobalt particularly. And that's because of the lifetime of vehicles, right? So the plot on the left here, I'm showing the potential secondary cobalt supply for a couple different scenarios, different compound annual growth rates in electric vehicles, as well as different lifetimes of the vehicle pack, 8 to 12 years. And so in this shorter term, this 10-year time horizon, it's difficult for recycling to play a significant role. The role becomes more significant beyond 2040, right? As we have increased growth, which we would want in the case of decarbonization, that's going to mean that it's more difficult to meet demand with secondary supply. But what it also means is that it's important now to invest in the infrastructure, which gets back to some of the challenges that Chris outlined in terms of difficulties in investment in infrastructure, particularly domestically, particularly given the current economic situation, to think about what our battery recycling infrastructure should look like. And on the right-hand side is a schematic from a group at Argonne that started up some significant work in what's called direct recycling. So folks are maybe familiar on the recycling side with more high temperature based, this pyrolytic processing of battery refining versus hydrometallurgical, so more chemically derived recycling versus direct recycling. And in the case of direct recycling, that's trying to re-lithiate, so reconstitute a cathode material so that it could be used more directly back in battery manufacturing, hopefully preserving some of that value. So while it's challenging for recycling to play a role in the immediate, we do need to be thinking about it in terms of the longer term investment in order to have that, as the batteries are coming back, to be able to meet the demand for along the material supply chains. So with that, I'll just leave you with some summary thoughts here. In particular, as I'm focused on the materials aspects of these, the substitution potential, how we extract these materials, but they need to be taken in context with the overall supply chains for how those materials are used and how that might have significant implications on our ability to move towards technologies at a pace we need to in terms of decarbonization. Thank you so much. I'm happy to take, I think I have about a minute for questions here, so thanks so much.
Okay, thank you very much, Elsa. Great as always. So one question that came in already was concerns recycling in other areas besides batteries. So for example, as we build out these large wind and solar systems, wind turbines or wind blades will get decommissioned at some point. Do you see some opportunity for recycling those wind turbine blades? Could they be used as structural members in other applications? The person who asked the question was thinking about replacing telephone or concrete light poles or something like that. But
Yeah, I mean,
structural members more generally, maybe.
Yeah, I think that there are opportunities. Structural applications become more difficult right now. The way we deal with those composites is not repurposing them towards structural things. So I think a little bit kind of related to those circles that I was showing is kind of the less the more we can focus on disassembly. So talking about designing those renewable applications to be then repurposed towards other applications where we think about that ahead of time, the better. But there is some work, particularly around wind blades, in terms of trying to do that recovery. So I do see that potential, but there's still a lot of opportunity, particularly linking that with the manufacturing, right? And for components that are that large.
Yeah. Do you have time for one more question?
I think quickly, yes.
Okay. So you talked a lot about the chemicals in the batteries. Some of those chemicals are fairly expensive, as you discussed. Do you see it as the drive for lower and lower cost storage becomes more urgent? Do you see perhaps a shift to other battery materials that might not be as energy dense as lithium-ion, but are cheaper, right?
Yes, yeah. So I didn't get into this, but making, and this has come up in the future of storage study, obviously, is trying to think about the applications relative to the sorts of trade-offs we could make in performance. So something that doesn't need as much energy density, like a grid-based application, could move to something like an iron phosphate chemistry. And we're starting to see that, where there we want to think about that in terms of lifetime cyclability of those, and so making those trade-offs where we're thinking about the supply chains and context, how those might shift, and having the right technology for the right application. Definitely starting to, that's always been in people's minds, but trying to think about that more as the pressures become greater.
Great. Thanks so much.
Thanks, everybody.
Okay.